All right, so far we've talked about how we have proper rotations, and these are the rotations you can carry out in kind of a physically manipulatable fashion. If we're going to pick up a molecule or a structure and turn it, these are proper rotations. Now, improper rotations are are a much more complicated set of symmetry operations. These are very hard to see, and so you just have to practice these a lot. And the reason that these are hard to see is because there are actually two existing symmetry operations that we already know that are done together. So sometimes these are called rotation reflections. And these are not separate operations, right? They are occurring together. So if we imagine that we have a principal or a proper rotation that's occurring, and then following that proper rotation, we perform a mirror plane that is a horizontal mirror plane to that proper rotation. So it's kind of like a CN, whatever that rotation might be, followed by a horizontal mirror plane. And this gets the name S sub n. And so this is for our improper rotation. And this n is the same type of n that we would use for proper rotations. The way that you can kind of visualize this, if you're having trouble seeing where these come from, is if you imagine you get a paper plate and you stick a pencil straight through the middle of the paper plate, right? The pencil would be your proper rotation. The plate itself is your horizontal mirror plane. So we're going to use our same example of cyclobutane as we investigate and practice these proper rotations. Except now, in order to better see these, we're actually going to look at the hydrogens and not just the carbons. It would be hard to identify this based on only the carbons. So here I've labeled my hydrogens as A through H. I've kind of labeled the ones on the top face of the molecule using A, B, C, and D, and the bottom face of the molecule as E through H. Now the reason for this is when we look at a three-dimensional structure, we can go ahead and label these A, B, C, D, E, F, G, and H again. And in order to simplify this drawing, what we're going to do is we're instead going to use a kind of rectangular prism. So this structure over here on the right. So these are equivalent structures. All I'm using is this rectangular prism to better identify and draw out this molecule. This is a way that we can skip using all those dashes and wedges and instead kind of use a shape. So if it is helpful to you, you can find something around your house that is kind of a rectangular prism shape that might help you kind of do these physical rotations. So for right now, what I want you to do is make sure that you're comfortable with how we get from this location on our picture that is labeled A up to this top left corner A. This labeled location E down to our bottom left corner E. Make sure that you can understand these assignments on the box. So pause the video if you need to, make sure you understand these assignments. So now what we're going to do is we're going to look at a number of these improper rotations. So again, an improper rotation gets this S sub n, and this is a proper rotation plus a horizontal mirror plane to that rotational axis. So the first thing that we actually have to do is do all of our proper rotations. So this top line here, these top four boxes, we should be able to do just using our normal proper rotation. And what we're going to be looking at here is a proper rotation that essentially goes straight up through the middle of the box, right? So this is going to be our z-axis. This is our principal rotation axis. It doesn't have to be, but in this case, it is our principal rotation axis. So around this axis, we should be able to fill in these structures. So what I want you to do is, again, pause the video and try to fill in these other three structures on the top of the box, following our three different C4 rotations. Hopefully, after doing these proper rotations, you're able to get these boxes along the top. So this was the proper rotation component of our improper rotation. So the next thing that we need to do is carry out our reflection, right, our sigma h, on each one of these structures, right? So what we're going to be doing is a sigma h that essentially cuts this molecule right in half, right? This is the sigma h that actually exists for the molecule as well. And so what we're going to do now is we're going to look at what happens to each one of these steps as we do this drawn sigma h, right? The same exact horizontal mirror plane straight across the board. And so for this first example, right, this is actually just a sigma h, right? It's actually not nearly as exciting. And that's because what we did here was essentially a C1 plus the sigma h, right? You could also think of this as the identity plus the sigma h. And so these are just the horizontal mirror plane, right? So this is not a new operation. This is the same as the horizontal mirror plane that we already have described. And so if we're going to go ahead and look at what happens here, we end up with E and A switching places, F and B. So we can go ahead and fill this out straight around the box, right? And so this is just our boring old sigma h. This is not a new operation. So if we move over 1, right, and now we're looking here, and we perform our sigma h, what this operation is this was now a C4 plus that corresponding sigma h. So this is going to be a new operation, which is an S4. So if we were going to go ahead and flip our labels here, we would have A, B, C, and D, E, F, G, and H. So this is that good old rotation reflection. And this is, again, a new operation. Right? So this is something we can add to our list, is a new operation, which is this S4. So what happens if we do it from this third rotation? So we know, again, from what we looked at earlier, that this is not really a C4, right? This is, in fact, a C2. If we do a C4 twice, we end up just doing a C2. So what we're looking at here is a C2 plus that corresponding horizontal mirror plane. So let's see where our labels end up. So we end up with A down here in the bottom corner, B, C, and D, E, F, G, and H. Now, this looks like a new operation. That would be like an S2. However, in fact, if we look at what happened, everything moved to the opposite corner of our box, right, of this rectangular prism. So A went from the top left to the bottom right. E went from the bottom left to the top right. So this is actually not a new operation, at least in terms of what we've defined, but this is actually an inversion center. So S2 is really inversion, right? And this is just the way that this operation works, is that if you do this rotation about 180 degrees and then rotate through the horizontal mirror plane, you end up just performing an inversion. So this is something that we have to add to the list, but it's actually not an S2. Right, so we have a few special cases here. So we see that a sigma h is actually like an S1, right? So it's like a C1 and a sigma h. We see that an inversion is really like a C2 and a sigma h, right? So inversions are just S2s. So let's look at this final case, right? So again, this was a C4 plus that corresponding sigma h. And so if we were going to carry this out, we end up with A, B, C, and D, E, F, G, and H. And this is, in fact, a new operation. This is an S4. We don't have this anywhere else on our list. And so if we're thinking about the operations we have to add to our list, we have to add two S4s, right? Two S4s, and this inversion center, which we know now is an S2, right? But we have a better, more complete way of describing this. This is a special operation called the inversion. And so we can add these to our growing list, and this now describes all of the symmetry elements that we have for cyclobutane. So if we look at this completed list, right, we end up with the identity. We have two C4 rotations that are that principal rotation axis. We have the C2 that comes from the principal rotation axis. We have two C2 primes. We have two C2 double primes. Again, both of those are not contained within the principal rotation axis. We do have a horizontal mirror plane, a sigma h. We have two vertical mirror planes and two dihedral mirror planes, And now, with our improper rotations, we can add an inversion and two S4s to our list here. And so if we count up the total number of symmetry operations that can be done on cyclobutane, we end up with the number 16. This is what we call the order of our system, and it describes the total different possible symmetry operations that can be carried out. So the higher this number is, we would say it's the greater symmetry of a system. So we can now actually quantify which compound or which system is more or less symmetric in comparison to each other. So this is going to be a vital skill for us moving forward. So from here on out, you really need to be able to identify that principal rotation axis kind of at a glance. So you need to be very comfortable with identifying the principal rotation. And then you need to be comfortable with looking for given symmetry elements. So if you're told that there's a C2, you need to be able to find a perpendicular C2 or one that doesn't lie along the same line as our principal rotation. You also need to be comfortable with this idea of these reflections, and whether they are the horizontal reflection or vertical reflection will become very important. The improper rotations are again very difficult to see, but you should be able to perform them on a structure, and you should also be able to show that the inversion and mirror planes are really just special cases of improper rotations, right? So we can kind of group all of these up here, right? These are all improper rotations. Even if we aren't going to call some of them improper rotations, we now know that they are, right? So we know that all the sigmas are an S1, inversions are S2s, then anything else gets its normal S with the sub n subscript. All right, so keep practicing identifying principal rotational axes and keep practicing identifying all these different symmetry elements in a given compound.